Good morning, everyone. I am Carlo, and today our team, Rodrigo, Fernando, Diego, and I, will present our final project, a modular heavy transport assembly. In simple words, we designed this heavy truck from scratch to show you how to use 3D printing from industrial parts. Our main goal was to design a complex machine, prepare it, and actually print it, making sure all the different pieces perfectly together. Why did we choose a truck? Because it is the perfect model to test real engineering concepts. As you can see in this slide, we want a balanced, complex design with easy printing. We use automotive concepts to build the chassis and the wheels and aerospace principles to make the parts lightweight but strong. Most importantly, we use DFAM, Design for Additive Manufacturing, strategies. This means we design and separate the truck into pieces to avoid printing errors, use fewer supports, and save material. For example, designing a multi-part assembly like this requires very precise engineering tolerances. We had to calculate the exact space between the pieces so they will connect perfectly after the plastic cooled down. Also, every curve and angle was planned for overhang minimization, which basically means designing the shapes so the 3D printer can build them naturally without wasting time and plastic on extra support structures. So this is the big picture of what we built and the engineering principles behind it. But how did we actually do it in the computer? Now I will pass the floor to my teammate who will explain our digital architecture and how we cemented the model in SolidWorks. Thank you.
Then we have component segmentation. Well, this is a very important part of our work because it shows our strategy. We design everything in SolidWorks, but then we have to think about how to split the model to make it printable. Because we didn't print the truck in one single piece. Instead, we use a strategic segmentation. For example, look at the cab. We separated it to isolate the complex details, and we made it vertically. This improves the resolution and makes the surface look a lot much smoother. For the chassis then, we decided to split them along in the middle. This way the material is much stronger and can support heavy loads without breaking. And finally we have the wheels. Well, the wheels were printed one by one to ensure that they are perfect. Then we have the digital to physical plan. Well, the process of bringing our digital design into the real world, we have to follow a 4-stage plan to ensure quality. Well, first of all is CAD because we use SolidWorks for the making and to verify that all the pieces fit together in the assembly. Then we have to export and verify it. We export the files to STL format, so in this step we checked for mistakes and made sure the wall was great so the parts wouldn't be too soft. Then we have slicing. Here we use a software called Ultimaker Cura and then we have only with the software. And finally we have the G-code generation. Well, this is the final step where the computer creates instructions for the 3D printer to move and create our truck. So, thank you.
This project delivered hands-on experience in design for additive manufacturing, multi-part CAD modeling for 3D printing, print orientation strategies, support management, slicing and G-code preparation, post-processing techniques, tolerance consideration for printed parts, and iterative refinement. Significant independent learning occurs in additive manufacturing workflows, material behaviors, and optimization of the FDM technology. Large language models provide valuable supports for troubleshooting and refinement with prompts properly documented. Also, this project reflects principles used in additive manufacturing applications for heavy-duty transportation vehicles, modular structures, and custom components in the automotive sector. It also demonstrates aerospace-relevant concepts such as lightweight segmentation, complex geometries, and manufacturing designs, highlighting the value of this DFAM in modern industry productions. And as a conclusion, we can see that our Optimus Prime inspired mechanical truck assembly successfully achieved the goal of designing and preparing and producing a multi-part system through this additive manufacturing into a single integrated unit. This project combined all this CAD modeling, strong the FAM application, the FDM 3D printing with ABS materials, and post-processing while reinforcing key principles for transportation and aerospace industries. Through iterative development and complete additive manufacturing workflow, the concept was transformed into a physical, functional deliverable. This experience strengthened our practical skills in additive manufacturing process for digital preparation to final production and a very reasonable cost.
Synthesizing DFM for heavy industry. In this section, we analyze how design for additive manufacturing is being synthesized for heavy industry applications. The goal here isn't just 3D printing parts, but fundamentally rethinking mechanical architecture for better performance. In automotive scalability, looking at our modular truck body example, the project demonstrates its self-direct scalability for the automotive sector. By utilizing a multi-axle setup, we can rapidly prototype custom commercial components and complex chassis configurations that would typically require expensive, long-lead tooling. For aerospace scalability, we apply these same principles to the aerospace sector. Through lightweight segmentation and integrated assembly, we prioritize weight reduction and precise multi-part integration, key requirements for modern aerospace structural architecture. And ultimately, this project validates the entire digital to physical workflow by moving from multi-part CAD directly to ABS FDM production. We've proven both the economic and structural efficiency of additive manufacturing for complex mechanical assemblies. FDM production and economics dashboard. Now, let's take a look at the operational and economic data behind this production process. Efficiency is a major highlight here. Small components are completed in just 1 to 2 hours, while larger segments take between 4 and 6. This brings our total cumulative print time to between 18 and 24 hours, a very competitive turnaround for a full assembly. We select FDM ABS for this project due to its high mechanical strength, superior thermal resistance, and durability during post-processing. The total material usage for this build stays within the 400 to 16 gram range. Finally, the financial breakdown confirms the viability of this approach, with material cost between $8 and $18 and machinery cost under $10. Our total assembly cost lands between $15 and $30. This proves we can achieve high-fidelity function prototypes at a fraction of the cost of traditional manufacturing methods.